Hello and welcome to the Chapter 3 podcast on Section 3.4. Today we're going to be talking about Avogadro's number and the mole. Avogadro's number is basically a subjective number. It is based upon 12 grams of pure carbon, 12, and remember 12 refers to the mass number, so this is a particular isotope of carbon. So if we actually estimate or count the number of atoms in 12 grams of carbon-12, it is 6.02 times 10 to the 23rd atoms. But moles can mean things other than atoms. They can mean something known as a representative particle. Representative particles can mean different things depending upon the substance, and we'll talk a little bit about that now. So in the first example here that you see, we have 1 mole of carbon-12 atoms. So in that case, we have 6.02 times 10 to the 23rd atoms. So atoms is one way to represent to refer to a representative particle. We can also have a mole of water molecules, and if I have a mole's worth of water molecules, that's referring to the molecule as a unit, not the individual atoms in the water. So I can also say I have 6.02 times 10 to the 23rd molecules of water. So molecule can also be a way to represent a representative particle. We also have nitrate ions. If I have 1 mole's worth of nitrate ions, this is 6.02 times 10 to the 23rd ions. So ions is another way to refer to a representative particle. And then the one that's not listed here is formula units, and those are for ionic compounds. And that's again another more specific way to refer to a representative particle. You can do calculations with Avogadro's number where we can convert particles, representative particles to moles, and moles to representative particles. And basically we're going to use the dimensional analysis that we talked about and used in the earlier part of the course when we discussed measurement conversions. And if you think about it, all Avogadro's representative particles and moles are different units of measure, and basically we're just doing a conversion. So if I want to go from moles to representative particles, if let's say I gave you 4.5 moles of methane and I asked you how many molecules there were, notice how we set up the dimensional analysis in such a way for the moles are in the numerator and the denominator, much in the same way we did our metric conversions a while back. So moles would cancel out, leaving me with the unit of molecules, which is what I want. MOL, by the way, is the abbreviation for mole. I know it's kind of dopey, but that's what it really is. And we find that there are 2.7 times 10 to the 24th molecules in 4.5 moles of methane. We can also go in the reverse direction where I give you representative particles and you calculate moles. So in this case, if I give you atoms of gold, again, we flip our fraction compared to what we did in the first one, and we divide by Avogadro's number as opposed to multiplying, and we find out that 1.25 times 10 to the 24th atoms refers to 2.07 moles of gold. We can also calculate atoms within representative particles that are not atoms. So I can figure out how many atoms there are in a molecule or in an ion or in a formula unit. So this is shown here in the last example where I have 1.50 moles of sodium carbonate to begin with. So if I want to know the number of atoms of, for instance, oxygen in this case, I first have to calculate the number of formula units of sodium carbonate there are first. And so notice how moles cancel out. Fu is short for formula unit. If I stop here, I just have formula units. I want atoms of oxygen. And we see that for every formula unit there is of this sodium carbonate, there are 3 atoms of oxygen. And so our final answer would give us atoms of O. And sometimes we may be interested in a specific element within a molecule, formula unit, or ion. So just something to keep in mind. We also have molar mass. So we can also relate moles not only to representative particles but also to mass in grams. A mole is basically just like a number. So if I say a dozen, it's a number of something. Everyone knows what number that refers to. So a dozen is like 12 of something, right? And a mole is like 6.02 times 10 to the 23rd particles of something. Now, I can have a dozen cars and a dozen donuts, right? The number of them are the same, but they don't weigh the same, right? Just similar to like with atoms, I can have a mole's worth of hydrogen and a mole's worth of lead, but they do not weigh the same. They have different AMUs, so that's why the mass has to be considered, not only the amount. What we find is that the mass of an element in AMUs is basically equal to the mass of 1 mole of that substance in grams. So that's one of the reasons why Avogadro's number is the number that it is. It allows us to use the same number for atomic mass units as well as for grams, referring to a mole's worth of something. Okay. In this figure below, or we'll start with this first one. So if I have a molecule of H2O, see how it weighs 18 AMUs? If I have 6.02 times 10 to the 23rd molecules of water and we added it up, if we add up the mass of that, it adds up to be 18 grams. So the 18 and 18 are the same. The only difference between the molecule and the mole's worth of that is the unit of measure. And then you can also kind of see that in the thing below. So notice the atom, atomic nitrogen, is 14 AMUs and 14 grams, whereas molecular nitrogen, remember it's diatomic, so it's double the weight, not only in AMUs but also in grams. We can also look at this in terms of representative particles. So if I have a mole's worth of nitrogen atoms and a mole's worth of nitrogen molecules, in terms of numbers of general representative particles, they'd be equal. But if we compare atoms to atoms, notice how the nitrogen atoms for N2 would be doubled, which makes sense because of the formula itself. If we compare ions, ions are basically identical. And then for compounds, again, the mole refers to the formula unit, but we can also break this down in terms of positive and negative ions that make up this particular formula unit. So we can have barium, but notice that we have twice the amount of chloride ions, which is shown here. And this is something we'll work with more in class, so you can kind of get a feel for some of these numbers. Here's an example of calculating molar mass. Sometimes this is called formula mass if we're talking about formula units, or sometimes it's called molecular mass for covalently bonded compounds or molecules. But either way, it's the same. It's actually the same as calculating formula weight. It's just that instead of AMUs for our atoms, we now have grams. So basically, we're going to find the mass of each element on the periodic table. Then we multiply by the number of atoms within the formula of the compound, and then we add the products. So in this particular formula for calcium nitrate, there's 1 mole of calcium atoms, and this number, the 40.078, I got from the periodic table. There are 2 nitrogen atoms, because remember the 2 we multiply inside the parentheses. So this is 2 times the mass of nitrogen, and there's 6 oxygens, so 6 times the mass of nitrogen. And then we sum these products. So the mass of 1 mole of calcium nitrate is a little over 164 grams for every 1 mole. And then we can use this to do some other things. So we can use molar mass to do other conversions besides moles and representative particles. We can also convert moles to grams as well as grams to moles. So if we want to convert grams to moles, if in this example they give us 508 grams of sodium hydrogen carbonate, well, the first thing we need to do is we need to figure out how much a mole of this NaHCO3 actually is. So that's where this 84.6 comes from. It's the sum of the sodium plus hydrogen plus carbon plus 3 oxygens. So it's 1 mole over this, and the purpose of that is to have the grams cancel, leaving us with a little over 6 moles of sodium hydrogen carbonate. We can also go in the opposite direction, where if I give you moles, you can calculate grams. So here I give you 6.33 moles of NaHCO3, and now again we're going to use the same molar mass, because it's the same compound, calculate the same way, and now we're going to multiply as opposed to divide, and see how the moles cancels out, and leaves us with 532 grams of NaHCO3. We can also do Other conversions, if we want to go between grams and representative particles, the mole is our bridge in order to do this, and I'll kind of give you a visual of this when we do our discussion in class. Again, we're going to use dimensional analysis in order to do this because it makes the most sense, and we're actually going to need dimensional analysis to do some more complicated things with this stuff a little later in this chapter. Formula units and represented particles are normally large numbers, so if you get really large numbers with mass, like times 10 to the 23rd, there's a good chance that you messed it up. So it's something to kind of keep in mind as you do it. Grams and moles are normally smaller numbers. You're not going to really see numbers like times 10 to the 23rd or anything ridiculous like that. So keep that in mind. So here's some examples of some more advanced mole calculations. And again, we're going to practice this a lot in class, so these are just for reference. Let's say I ask you how many molecules there are in 4.2 grams of HNO3. There's no way to go directly from grams to molecules, so we're going to have to convert to moles first. So what we're going to do is we're going to go from grams to moles and then moles to molecules. Okay, so if I'm going to go from grams to moles, I first need the molar mass of HNO3. So the 63.0128 is the mass of H plus N plus 3 times O. If I'd stop at this point, my final answer would be in moles of HNO3, and I want molecules. Molecules is not the same as moles. So because I'm going from moles to a representative particle, I need Avogadro's number. Okay, and again, it goes on top because I want moles to cancel, leaving me with 4.01 times 10 to the 22nd molecules of HNO3. And again, this makes sense because remember, representative particles should have big numbers like this. How many O atoms are in the sample above? So again, this is another advanced type of question where if I want to know how many atoms of O there are, we can look at this compound and we see that there are 3 oxygens for every molecule, giving me this many atoms of O. And until next time.